Welcome back. Let us resume our discussion on the latch circuit that we are looking at, transistor level implementation of the latch and the flip-flop. So, we started with the simplest latch circuit, which is just having a switch along with the capacitor, and this can fairly well act like a simple latch. When the phi 1 is on or the switch is on, the input level VDD or ground will be sampled onto the capacitor. So, this is a single latch which is level sensitive latch. Out of this, if we want to construct a flip flop, I can cascade two such latches. So, I can go ahead and put two such latches in series, just like we did for the block level implementation. So, I can put two transmission gates you can have, as I said, you may not even need a dedicated capacitance, this may be just a parasitic capacitance coming because of the MOSFETs, and you can have another second latch which is driven by phi 2, and phi 1 and phi 2 can be just the opposite phases of the clock. So, if you want to have positive edge triggered flip flop, I can keep phi 2 as the positive pulse of the clock or the level 1 of the clock. So, correspondingly I have the transistor level implementation. Sorry, we are supposed to make the transistor level implementation. So, let me so this is a simplest possible implementation where you can just a minute, let me. So, this is the simplest possible implementation that we can have. You have the input clock sampling the data at CP. So, during the positive phase of the clock, you can have the phi 1 over here, phi 1 bar over here, and then you have phi 1 bar over here and phi 1 over here. So, you can have during the input during the high level of phi 1, you can have the Tg1 which is transparent and Tg2 which is off. As a result, the input data is sampled at the CP, whereas when the opposite phase is on, that is the phi 1 is low and phi 1 bar is high, this is going to be on and this gets off immediately. As a result, the data is going to be the same value that was stored at CP will be transferred to the voltage, the capacitor over here. So, this can be a possible simple implementation, but what are the issues over here? Can this work reliably? Is there any issue that we see in terms of data transfer? So, from V in to the CP and then from the CP to the final capacitor over here, which can also be CP. This is just we are relying on the parasitic capacitances, we are not putting any additional intentional capacitance, because in general you can have a large number of registers and flip flops in digital design, and if you start putting capacitances for each of those, it is going to take a huge amount of area. For analog blocks, they are fewer in numbers in the front end, so you are needing few big capacitors to implement them, that there was just few in count, whereas digital units can be large in number. So, you need a huge number of registers and flip flops, and of course, we cannot afford to put these CPs or additional dedicated capacitors, we can rely on the MOSFET capacitor. So, now what is the problem here? If I look at the overall operation, ideally if this voltage is in the first phase getting charged to VDD by the input, and next I am putting this latch on, what is the voltage I expect here? Is it going to go to VDD? So, phi 1 phase I charge this to VDD, and in the phi 2 phase this was disconnected and this was turned on, and therefore, we expect certain voltage over here. What is that voltage? Is it VDD? VDD by 2, because the charge sharing will take place and the total capacitance has been increased. So, whatever was the initial volt charge on the capacitor, CP times VDD was the charge, and once you disconnect this, that charge is now preserved, that is not having any path to go. As a result, now if this was initially discharged to 0, depending upon the voltage over here, suppose this was 0, this will go all the way to the total charge being constant, it will be 2 Cp times VDD or 2 Cp times V out, and the result V out will be VDD by 2. Of course, you can have some different voltage stored. You can, in the previous phase, you can end up having a different voltage. As a result, it will depend upon the previous voltage. So, this has to be in general equal to Cp times VDD plus Cp times V out, and accordingly I can find out what is the V out level. So, definitely this is not going to solve the purpose. We are not going to get the same voltage level as we expect. So, in order to preserve that, what can be done? What can be added to this latch circuit, so that I can always ensure that if this level was sampled to be VDD, the final level over here is also coming as VDD, or if this was sampled to be ground, the final level over here is also coming to be ground. So, in that case, I have to decouple these two capacitors. I cannot directly couple the capacitor over here to the capacitor over here using this switch. I need to decouple that. One way to do that is to put an inverter over here. If I put an inverter, then I am able to comfortably decouple the latch. Likewise, the input of this latch can be coming from some other latch or some other logic gate. There also I would not like charge sharing with the input device. So, once again I would like to put an inverter over there. So, I can put one inverter here and I can put another inverter over here. So, that the capacitances over here are not directly coupled to the capacitance on the other side. So, in order to arrive at the latch circuit, I can put inverters after or before. Suppose you are putting it before the, and so if we have to go for, say, later we will see that putting the inverter after the switch can have some advantage, because there we can apply some feedback configuration. So, let us go for the switches and go for the inverter over here and another switch and another inverter over here, and then I have the parasitic capacitance over here, which is given by the parasitic capacitance of the transistor at this point, and likewise you have some parasitic capacitance over here, Cp, Cp, and these two switches are once again controlled by phi 1 and phi 2, which can be just phi 1 bar. So, by phi 1 bar means if this is the clock phase, the high phase of the clock, phi 2 can be low phase of the clock, that is it. And these are the parasitic capacitances constituted by this MOSFETs and the inverters and so on. So, now at least I have been able to decouple the two capacitances. If I am sampling VDD over here and after the phi 1 has gone low, the VDD voltage will be retained over here. Of course, there will be some leakage and some disturbance, but to a significant extent, the drop may not be very large and VDD will be retained, and as a result the output will be driven to low. Output of the first inverter will be driven to low, and therefore, when you close this switch, that low level is coming to the Cp. Transistor level, what is happening? Of course, we should have that picture in mind, that what is happening at the circuit level and which transistor is getting on, what is the discharge path, what is the charge path, and so on. So, this is the transistor level picture. You have the phi 1 bar. So, phi 1 bar means just the opposite phase of the clock. This is phi 1 bar and this is phi 1, and this is your D in and this is your Q. So, of course, we have two inverters now in chain. So, the polarity of D in and Q is going to be same. If the D in is 1, the Q is also supposed to be 1. So, that behavior is of course maintained, and when the phi 1 phase is on, this transmission gate gets on. I can call it TG1. TG1 gets on, and the D in is stored over here, and during that phase this is off. The TG2 is off, and as a result the output of this inverter will be D in bar. So, this will be D in bar. So, this D in bar is remaining transparent to D in during the phi 1 phase. If the D in is changing, the value over here will also be changing, and in the phi 2 phase this gets off. As a result, the value of D in stored over here becomes clamped, because this, after this getting off, whatever voltage was stored over here and this parasitic capacitance of this node will be remaining stationary, and as a result this will be the sample Dean value, and hence this will be the sample Dean bar value. If this was VDD, this will remain VDD and this will remain 0, and the moment if this remains VDD, that means this MOSFET will be on and it will be always shorting this point to ground, and the moment this latch goes on, because this MOSFET is on, it will also discharge this node to ground. As a result, this will also bring the same value logic level 0 over here, and as a result the output will be going high. So, that is the overall operation. Phi 1 phase, this node, the parasitic capacitance at this node Cp, I can draw it upwards. So, this is the parasitic capacitance Cp at this node. So, once the switch is getting off over here, this Cp is storing the charge VDD times Cp if the input level was VDD, and that is keeping this transistor the NMOS in on state, and as a result this particular node is pulled down all the way to ground. And likewise, when the Phi 1 phase is low, or you can say the Phi 1 bar is going high, this switch gets disconnected, and as a result whatever data was stored over here on the Cp, that is retained. If this was 0, this is retained as 0. So, these are the two nodes or the parasitic capacitance, and these two nodes are essentially doing the role of storage. They are basically storing the charge in this particular configuration of the latch. This is clear. Now, of course, as we saw that we are not going to afford, we may not be able to afford dedicated capacitances over here, and the leakage can become dominant. It can end up having a significant droop if you are having a lower clock frequency in the system and you want to keep the data stationary for a long duration, it can be a problem. If you are having a faster circuit or a faster logic, then this configuration can work, and people do use this flip flop configuration wherever fast operation is required and you do not need to retain the data for a long duration. But in cases where the data has to be retained for long duration, it can be a problem. For example, if you look at the counter that we are trying to build and the last logic level that you have, there you can see that the counter level or the output level is maintained for a long duration. So, the entire sampling duration, we have these Ts, the sampling pulses Ts, or we can have called them Phi 1 in our case, and then you have this the clocks coming in between, which is basically let me distinguish this from the Phi 1 here. Here I have used Phi 1 just for the clock, and here let me call this Phi S, the sampling phase, and this is the Phi, I can say Phi conversion phase, where the ramp is happening and you are converting the data. So, for this entire duration, the MSB of the counter, it stays 1 for half the duration, 0 for half the duration. Therefore, the data is retained for a long duration for the MSB counter. And likewise, of course, in this particular example, in general we are having lower clock frequency. As a result, there is a significant deviation in these voltage levels can be expected, especially if you look at the last flip flop, that is MSB flip flop of the counter, definitely that is having the longest duration of the data retention. It is storing the data for almost half the duration of this entire Phi C, and as a result it can have maximum amount of deviation on the MSB level that can end up discharging significantly for the same dimensions of this parasitic capacitances. Therefore, especially in low frequency operations, we may not really rely on this particular configuration of the flip flop, where we are using these parasitic capacitances to store the charge and retain the logic level. Rather, we would go for a system where we can have storage mechanism inbuilt, and we can have some mechanism through which we can ensure the retention of this logic state independent of this parasitic capacitance value. And there we utilize the concept of positive feedback in this circuit. So, let us see what is the concept of positive feedback and how it can help us in implementing a stable storage element, which is not only used in latches and flip flop, but it is also used in designing memories, semiconductor memories, which are basically SRAM integrated onto your chip. Any question before we proceed? So, if we consider this inverter as an amplifier, we know that in the this has to be ground. So, suppose by some mechanism I am biasing this inverter in this mid region, so that it is in high gain region, right. This is what we do while operating common source amplifiers, or so there we ensure that the input is biased such that the biasing point is in this high gain region. Suppose we do the same for this inverter, because through some mechanism we are able to bias two inverters which are connected back to back. Output of the second inverter is connected to the input of the first one, and the output of the first one connected to the input of the first one. Suppose we are able to bias both of these inverters in this high gain region, and then we apply some sinusoid signal at we suppose break this loop and apply some sinusoid signal at this point. What is the gain of that circuit? If we look at the overall behavior, we can just take superposition. You have the same signal being applied to the NMOS and PMOS for the first device, as well as the second device also having same signal. So, it is nothing else but PMOS and an NMOS common source amplifier tied together. I can take superposition and find out the V out as minus GM N times the RO over here, which is RO P parallel RO N of the output times V in. Likewise, you have the GMP minus GMP times RON parallel ROP times V in. I can just take superposition. So, you have, because of the first signal over here, I can assume that this is AC ground and then find out the expression for the output voltage. So, if I assume the signal is over here and put this to AC ground, and I have minus GMP times RON parallel ROP times V in signal coming over here. Likewise, second, if I assume that the signal is at the gate of the NMOS and this is AC ground, then GMN times RN parallel ROP is the signal over here, and I just add it together, and for both of them of course we are getting inversion. So, both of them have same effect on the output for a given input, and therefore, this is the small signal expression that I get. So, I can see this as an amplifier provided these transistors are biased in this region. I am not saying how they are biased. Suppose imagine you have some mechanism through which you have biased, and then I can ask the question that if you have this connection, can we see a positive feedback coming in? That means, if you, because of some reason, suppose this node voltage is going up, if this voltage finally also goes up, tends to go up further, that means it is going to support this transition from the initial point. Suppose the initial point was VDD by 2, it was a high gain region for both of the transistors. Suppose you initialize all these both these nodes of VDD by 2, and after that, because of some reason, because of some noise, this node voltage went up little bit by delta. So, what is the effect on the final node? Is it supporting the same direction of change, or is it suppressing that? So, here if you see, if this goes little bit higher than VDD by 2, this is going to go down by a larger amount, because you are in the high gain region, and as a result this is going to go up by a further larger amount, therefore supporting the same change. Therefore, we have a positive feedback established. Likewise, if it is going down, it will be going up, and it will be going down even strongly. Therefore, it will be supporting the same change or the same direction of change. Therefore, if you initialize this loop in the simulation, suppose you initialize this loop to VDD by 2 here and VDD by 2 here by some appropriate setting, you have some noise injected at some point. Depending upon the initial condition of the noise or the noise level here, positive or negative, the inverter can end up latching in one of the two levels, high or low, because of this positive feedback action. And once that is established, the levels over here are stored indefinitely. From the point of view of feedback, if I say, if I am looking at the common source operation, from here to here you have 180 degree phase shift, from here to here you have another 180 degree phase shift because of the inversion. Therefore, from this point to this point, of course, we have 360 degree phase shift, and we know we have discussed the stability criteria, and in the amplifiers we always try to avoid this condition, 360 degree phase shift and high gain, and therefore, we know that in this condition, for the omega or the frequency at which this 360 degree phase shift occurs, the circuit will oscillate. So, that is the omega oscillation of the oscillator. the frequency at which overall 360 degree phase shift across the loop is obtained, and if at that frequency gain is higher than 1, the circuit will oscillate. Here we have two stages, we are in high gain region, both of them, therefore, the overall gain across the loop is definitely higher than 1. But what is the frequency at which omega 360 degree is being reached? That is omega equal to 0, because we know that you have the parasitic capacitances of this MOSFET which are going to further degrade the phase at higher frequency. So, omega equal to 0, we have exactly 180 degree phase shift across this one, another exactly 180 degree phase shift across this one. But as we go towards higher frequency, we know that the first pole we have another 90 degree phase shift, second pole we have another 90 degree phase shift for both these inverters. Therefore, exactly 360 degree phase shift is achieved at omega equal to 0. As a result, what we are seeing is that the inverter is latching up to 1 or 0 or 1 at omega equal to 0, that means DC, it is not changing. So, that is consistent with our discussion on oscillation and stability. 360 degree phase shift being reached at omega equal to 0 and the inverter latching up at DC, one of them getting stuck to 0, another one getting stuck to 1, and therefore, storing this data indefinitely. So, this is the basic mechanism which is allowing us to store the data or save the data at these two nodes to either low or high or low indefinitely, as long as the power supply is given to these inverters. This is clear, the basic storage mechanism in the latch. In order to construct the flip flop out of this latch, however, we need to write into it, we need to deterministically write into the logic levels here and here. For that, we need to access these nodes and intentionally write logic high or logic low into them. For that, I can go back to my latch circuitry that I built, which was not having any feedback, and try to modify it, try to insert a feedback over here. Here we already have a driving mechanism. Here, if I insert a feedback for both these inverters and try to make sure that these are going to store the data, the data storage is not dependent upon these parasitic capacitances, we can make sure that the overall circuit operation is stable, the values are going to be latched and stored for a sufficiently long time. So, one way of doing that while ensuring the writability is to insert a inverter in feedback path over here and keep the feedback path off when the writing is going on at this node. When do we need the feedback? When do we need the feedback? Only when this is disconnected, so that this stored data over here is retained for long duration. So, when it is getting written or when this latch is on, we do not need feedback, because at that point I need this node value to be determined by the input value. But when this is getting off, then I need the feedback to retain this data. I need the feedback to be woken up and retain this data. So, a logical conclusion would be to add an inverter over here, and then put another switch and connect it over here. This switch should be driven by phi 1 bar. So, that when phi 1 is on, this latch, this gate is transparent, transmission gate is transparent, this node is connected to D in, the value over here is dictated by D in. This is not playing any role in determining the data over here. However, as soon as this goes off, I want to retain this data, I do not want this to be leaked because of the different leakage paths that we have in the MOSFET. As a result, I am turning on this feedback path, so that you are having a positive feedback in this loop and you are ensuring that this node voltage and this node voltage is fixed or clamped to the value to which it was written. If I do not do this, if I do not have this switch, if I just have this inverter, if I do not have this additional switch, then you cannot determine that when this node is, when this switch is getting on, this node can be driven by this inverter as well as the previous stage. So, I cannot determine whether what is the logic state of this node. It can be the previous stage, you have an inverter which is trying to drive this node to VDD, and at the same time you can have some other intermediate logic state which is being driven by this particular inverter. More severe condition occurs when you have the clock overlap, and you can have the logic stored over here trying to propagate through this inverter into this particular node. So, I would like this node to be dictated by the D in when the phi 1 phase is on and not by this path. This is activated only when required, when this data stored over here is supposed to be retained. So, my final implementation of the flip flop considering this topology would be including just another inverter over here along with the switch, and hence creating two latches which are having the positive feedback path activated at the complementary phase of the clocks. So, I can complete the overall latch, the flip flop circuitry. Or let me not draw the input state. I have the needs. Sorry, I have to let me redraw this, melt it up. So, you have the so this is our overall implementation where the data can be retained for a long duration. So, here I can start if it is a positive edge triggered flip flop, then I know that this second level is supposed to be triggered by the clock. So, I can say clock and clock bar, and then you have clock bar, sorry clock bar and clock. Likewise, you have the clock bar over here, the opposite phase, and clock here, and you have the clock and clock bar here. So, this is overall circuitry for the flip flop that we can have, which is robust enough and it is able to retain the data for long time, and it is not, we are not depending on the parasitic capacitance for sampling the data. So, I can call this as D and this can be Q, and also we can see that the Q bar is also automatically available. So, I can also use the Q bar over here. So, this inverter is also giving us Q bar. We will see that it may not be a very good option to use this as Q bar, rather than I can use another inverter to use Q bar. We will see that why. So, this is the overall edge triggered, positive edge triggered D flip flop that we are having, D Q bar, and you have the clock edge, and this is positive edge triggered. So, I do not put a bubble over here, and you have the input and output terminal. So, this is the basic building block of our flip flop, of our counter. Any question before we go further and try to characterize some of the delays and transition delays and related definitions for this flip flop, which can be useful for the design. Remember, while designing the counter, we discussed the clock to Q delay, which is going to determine how much is the ripple duration from the input to the output. So, we need to see what is that ripple duration, and likewise we also need to see two other very important definitions, the setup time and the hold time, which also plays very important role in operation of the flip flop. So, we are going to look into three important definitions: setup time, hold time, and clock to Q delay. Before we go there, any question regarding the basic operation and how we finally arrived at this flip flop circuitry, starting from the very basic definitions and assumptions. Of course, as compared to the dynamic, as compared to the flip flop where we did not have this feedback, as compared to the simpler flip flop where we did not have this feedback, we are having two additional inverters, and also we are having two additional transmission gates. So, from the point of view of clock, of course, it is having twice the capacitor. So, suppose there is a clock signal coming in. Ultimately, clock signal is also driven by some inverters or some buffers. So, ultimately a clock is a digital signal going 0 and 1. It will be driven by some inverters, and the clock over here will be going to all the different NMOS and PMOS. Likewise, you will have the clock bar. So, if this is clock, I can have the clock and clock bar being generated and being fed to all the different modules. In general, we would like the clock and clock bar to be exactly phase opposite, right. So, we would like them to be exactly 180 degree out of phase, but in general they have finite rise and fall time. So, the clock and clock bar, if I look at the actual picture, they will have finite rise and fall time. So, if this is clock, you can have clock bar over here, and in general for logic operation the delay is defined with respect to the midpoint of the transition. So, for example, if I want to see the delay of the inverter and I draw the two waveforms input and output, that is defined with respect to the midpoint. And so, if I want to characterize the inverter output, suppose this is the input waveform to the inverter having some finite rise time and fall time. So, the inverter will have some finite delay, because as we know when the input over here goes up, it will take some finite time for the NMOS to discharge it. So, it will be discharged completely after some finite duration. So, approximately once again it will be leading to a downgoing voltage over here, gradually only it will be discharged. So, it will have a slope, and with respect to the midpoint of transition of the input, it will have some additional delay. So, the input transition point, the midpoint of the output transition can be slightly away. So, this is the input of the inverter, this is the output of the inverter. Of course, it is 180 degree out of phase is inverted, but because of the finite delay of the inverter, you can have some propagation delay of the inverter. I can call it T delay of the inverter. So, generally we characterize the delays of the logic gates in terms of the distance between the midpoint transition. If this is the input rising edge of the or rising edge of the input of the inverter, it will the output will definitely fall as the input is going up, but it will take some finite delay because of the discharge path provided by the NMOS. You have a RC time constant, and the large signal operation, you are having ultimately this voltage getting discharged through this inverter through this NMOS, which is having some on resistance, and therefore, it is going to take some time to discharge it, and therefore, there is going to be some delay. And in order to characterize the delay, we have to look at the difference between the midpoints, and that is the way we define the delay of that inverter. So, in general, when we are looking at the characterization of these flip flops, there also likewise we have to look at the transition points and the midpoints of these transition zones to characterize the delay. So, before we go further, let us take a short 2 minutes break and then resume our discussion. So, before I go further and deal with the delays of these logic gates and finally characterize the flip flop in terms of these definitions, the setup time, hold time, and the C2Q delay, let us take a 2 minutes break and then resume our discussion on the characterization of the flip flop.